This is lecture number 8. In this lecture, we're going to talk about the timers and counters on the Arduino. This is a very rich subject, and in fact, we're not going to actually cover it all thoroughly in this lecture. We're going to talk about the most essential aspects of this. Some of this actually we're going to talk about more when we talk about interrupts, because that's really a significant application of the timers and counters. But we will talk in detail about many of the aspects of the timers and the counters. So just like we had with the GPIO registers that we worked with, so we will also have registers that we will be working with here in the timers and the counters. So we've already been using timers and counters quite a bit in our various exercises. So the commands, for example, millis and micros, these functions are use timers. In fact, they both use timer 0. The analog write function uses pulse width modulation. That uses a timer. The tone library we saw uses it, and the servo library also. So we've already been using timers and counters without really knowing what's going on behind them. The Arduino IDE is very good about hiding important features of various aspects of the hardware, but they're still there. Even if we don't understand them, if we don't know them, the fact is those aspects of the Arduino are still there and they're still in use. So in terms of timers and counters, we have these timers and counters. So timer 0, timer 1, timer 2. And so these are the pins to which they are connected. Their outputs are connected as an alternate function. Okay, and also there are, if you use a mega or a due, there are other timers that are connected as well. So notice that each timer has two channels, a channel A and a channel B associated with it. So that's something to keep in mind as we go through. We'll see how some of those things work. So notice that there are 6 pins connected up to the timers, up to the 3 timers, and those 6 pins basically correspond to the places where so in some cases where we have pulse width modulation actually being used. So 3, 5, 6. So these are some of the places where pulse width modulation is available. Okay, the initial timer state, timers 1, 2 are set and ready for analog write. That is, they're already set up to ready to use pulse width modulation. They're basically set to 8-bit pulse width modulation that is phase correct. We'll talk about what that means as we go along. With the clock prescaled to the system clock divided by 64. Timer 0 is also set to fast pulse width modulation for use with millis and micros. So associated with each register, each timer, we have various registers, quite a few registers. So we have the timer counter control register A and control register B. So those are 2 control registers. Those have some bits that need to be set in order to properly set up the timer or counter. There's also each timer, so the N here corresponds to which timer number we're working with. So I could have TCCR0A, TCNT0, so timer count. So this is, the timer will be counting up, for example. So it's being pulsed by a clock, and it will be counting up. And so the count value at any given time is given in this register. So for an 8-bit counter, it's just an 8-bit register. For a 16-bit counter, we then have actually 16-bit registers. Like, how does that work when you only have 8-bit registers? Well, it turns out it basically puts the 16 bits into 2 registers. And you can read each register separately, the high byte and the low byte. There's also the output compare register. We're going to talk about what this means for both channels A and B for each timer. Okay, so these are registers that we have, and then you also have some pins associated with each timer counter that are connected, that are at the output of these timers counters. So here is the overall block diagram for the timer and counter situation. As you can see, there's a lot of stuff going on. Okay, so we talked about the output compare registers. So here's output compare register A, output compare register B. So this is the nth timer. So this could be timer 0, timer 1, or timer 2. Basically follows the same kind of pattern. Here's the actual count that's used. So you have here control logic that actually that increments the count, that can reset the counter, or that can change direction. So it can count up or it can count down. You have a clock source that can be chosen, and there's also a prescaler that works together. So these two guys work together to form the clock that is being used in the timer and counter. Okay, we can talk about the top of a waveform, bottom of the waveform, and the compare of the waveform. Here's a waveform generator. Each of the waveform generator is basically generating pulse width modulation waveforms. Okay, so that's what the waveform generator is primarily geared towards. And then there are the bits, OC, the OC bit, output compare bits, coming from the waveform generation. Okay, and so there are the timer counter control registers, A and B. So there's a lot of stuff going on here. A lot of stuff going on, and it's helpful to see a diagram like this if you kind of know what's going on. For you to see this the first time around, it's like, wow, what is all that about? And is that all really necessary? Okay, so, well, anyway, yes, it is necessary, but you're not expected to like have all this stuff memorized right offhand. Okay, well, let's dive into timer 0, just as an application. So this is the timer used in most applications. It can be used as a simple counter. It can be used as a frequency generator, including pulse width modulation. It can serve as an external source for a clock counter, and it can generate tree interrupts. Okay, so tree interrupts are, well, let's talk about that. Here are the tree interrupts on timer counter 0. So we're going to talk more about this kind of stuff when we actually talk about interrupts. So this is just to let you know that whenever you have whenever you work with a system, you can get interrupts. So that's all I want to say about this for now. But there is, so that for a particular timer counter, the timer and counter basically is counting from the bottom, which is 0, up to the top, which may be 255. If it's an 8-bit counter, it'll be from 0 up to 255. And the compare register sees when there is when these two are equal to each other, it'll output something. It'll like toggle, or it'll do something to this bit when you have output compare register being compared with the count. The same counter or timer is being compared with another value, and you'll get something out coming associated with this. So these two guys together use the same timer, and yet can generate different signals, different waveforms associated with this. Okay, so it's important to understand OC, output compare register 0, channel A, output compare register channel 0, output compare register timer 0, register B. Here's the timer 0 count. Here's the output compare bit 0 for timer 0, register A. I'm sorry, not register, just channel A. This is output compare for timer 0, bit B. Okay, so there's a lot of stuff going on here, a lot of new terms, and so as we go through the Arduino, we find lots and lots of terms that are that appear that we need to be familiar with. So what do the registers do? A lot of registers. We've already seen a lot of registers. Okay, some of them set up the mode of the timer counter. Some of them set up various parameters of the timer counter. For example, the frequency at which the counting happens. Some of them provide output waveforms. Some of them provide options for comparing the waveform values with other values. So basically, a timer is basically just a counter with a clock input. So here, the clock can be the standard system clock for our Arduino, or it can be what's called a pre-scaled value. So it's that system clock divided by some number like 8 or 64 or something like that. That gives us a clock source. Or it could be some external signal, where you bring in an external signal and the counter then is just keeping track of the pulses of that external signal. So you can use it that way as well. It's less common to use it that way, but you can. You certainly can. Okay, we're going to talk about pulse width modulation, and there are two primary pulse width modulation modes. One is called fast pulse width modulation. The other is called phase correct pulse width modulation. The fast pulse width modulation, basically you have your counter that counts up and then it resets when it gets to the top, and then it counts up again and just continues. So that usage of the timer where it just basically continues counting up, it actually just continues counting up. And what happens when it gets to the top, it rolls over, and it's, again, you don't have to do anything special to get it to go to the bottom. The counter just automatically does that when it rolls over. Okay, and when it rolls over, it gives you a carry bit and all that kind of stuff. But you don't need to worry about that. It's just a counter, so it just counts and it just keeps counting, keeps going up and up and up. When associated with that timer, you have a value, compare value. When the value gets above, or actually when it's equal to this compare value, it will set the bit. Okay, so that's what happens when we for the fast pulse width modulation, and then when it gets to the top, it resets, it clears. Okay, so it sets when it hits that value, and it clears when it hits the top. Okay, and so a waveform like this would basically give rise to this. And so if this value is lower or higher, it will affect the width of the pulses. The phase correct pulse width modulation, on the other hand, instead of counting just up and then resetting, it actually counts up, then it counts down, then it counts up, and then it counts down, and so forth. And when you're above a value, you get a pulse of a particular width. So this is the pulse width modulation, the two different kinds of modes. So the phase correct pulse width modulation basically has the centers of these pulses evenly spaced, the centers. So the width may vary, but the centers remain evenly spaced. Whereas this, the falling edge of the pulse is those falling edges are evenly spaced. So slightly different. It turns out that for like controlling motors and stuff like this is actually a preferred way of doing pulse width modulation. So even though it looks more complicated, it's actually the preferred way. Overall, here are the primary modes of the of the timers and counters. So we have four modes. We have the normal mode, where basically the counter counts up to the max, which for an 8-bit counter is 255, then resets to 0. So that's the normal mode. And it turns out, even though it's called the normal mode, which is basically the simplest mode, it actually is not often used. It's less versatile to use that than it is to use some of these other modes. Okay, we talked a little bit about phase correct pulse width modulation. So pulse width modulation that is synchronized so that the center of the pulse is symmetric with respect to the timing clock, as opposed to fast pulse width modulation that goes as fast as the clock will allow. And it's synchronized with the falling edge, which the falling edge is not that significant of a feature, but that's how it's synchronized. And then we have the clear timer on compare. The clear timer on compare. So this is an important mode. The output of the counter is continuously compared with the output compare register, and the match can be used either to generate an interrupt or to toggle another signal. Okay, so all three of these use a compare value. It compares the timer with some value, and then when it hits that value, so it's basically counting up, and when it hits that value, it does something. So depending on what it does is basically what these three things are involved with. So in the normal mode, we don't have a compare value to worry about. These three guys, we have a compare value to be concerned about. Okay, so now how do we set up the timer or the counter to do the kinds of things we want to do? For example, to pick one of these modes, to set frequency, all that kind of stuff. Right? So, well, we first come to the timer counter 0 control register A. So here, this is just one of the timer counter registers. So it's a control register A. Control meaning it's going to be used to set up the timer and the counter. Okay, so again, notice that this guy is this variable name, TCCR0A, is actually a predefined variable in the Arduino, as are these bits predefined. So I have these COM0 bits for channel A and channel B. I have these WGM bits. So WGM stands for waveform generator. Waveform generator or something. Anyway, I have these two bits. So the COM bits basically control the behavior of the output compare pins A and B. Okay, so notice that the output compare pins on the ATmega 328 appear here for timer counter 0. They appear in port D, pins 5 and 6. Okay, so the COM bits control the behavior of these bits. The WGM control the function of those bits. Okay, so we'll see how all of this stuff plays out here. Okay. Okay. So the I see. Waveform generation mode. That's what the M was. Mode. So WGM bits, WGM 0, so that's timer 0, bits 0 to 2. Wait a minute. There's a bit 0, there's bit 1. Where's bit 2? Huh. Well, as I mentioned, the ATmega, they kind of picked some weird places to put some of the bits. Okay, so here's one of the bits, here's another bit, and you would think they would put, since there's a space, that they would put WGM02 right here, but they don't. Well, anyway, we'll find out where it is eventually, but for now, understand that somewhere on the Arduino is that third bit. Okay, so with the 3 bits then, we have 8 possible combinations for waveform generation. Okay, so here are some of those. Here are all of them. So remember, we had normal mode, we had phase correct pulse width modulation, we have clear timer on compare match, we have fast pulse width modulation, then we have phase correct pulse width modulation, and we have fast. Wait, how come we have 2 of these guys and 2 of those guys? Well, it turns out there's a good reason for it. So even though it's given by these names, there are actually 2 different ways of doing the same kind of function, and depending on which one you choose, you can get something else happening. Okay, so in this case, the top is 0FF, 255. So for these three modes, that's 255. For these three guys, we have the output compare registers. And notice we have output compare register A, not register B. So the A register is very critical for each timer because it actually sets up part of the mode of what's going on. Okay, so the update, the bits, this bit updates here in these two cases immediately. Okay, and here TOV0 flag, that's associated with that's an interrupt flag. So we're not going to talk about that so much right now, but that's associated with interrupts. Okay, so here in this fast pulse width modulation, it actually updates when you count past the top and reset to 0. Also, again, when it resets to 0. Okay, so here it updates on the top, and the top in this case is that. Okay, so in this case it's FF. Here it is the output compare register. Okay, well, so that gives you a basic idea of the things that are available. These two guys are not; these two modes are not used. Okay, so we have the COM bits, COM bits, and then the waveform generator mode bits. Okay, and these are the options that you get. So here we have normal operation, and in this case, the bit, the output compare bit, is disconnected. In this situation, again, we have normal operation, and the output compare bit is disconnected, and the output compare bit A is disconnected. Output compare bit B is reserved for something else. Okay, so in other words, you could actually use that bit for something else. So in this condition, with these COM bits and these waveform generation mode bits, we have this function. So again, this is under fast pulse width modulation. So we're actually considering fast pulse width modulation. In this case, it toggles on compare match, and this bit is reserved. In this condition, we have a clear on compare match. Okay, and the value is set on that value. Okay, and so this is a particular form of fast pulse width modulation, and this is the non-inverting mode, and then we have the inverting mode. Okay, so we have a number of different options for fast pulse width modulation. Okay, in this case, PC pulse width modulation means phase correct pulse width modulation, and again, we have a set of things that can happen. In particular, we have toggles that can happen on compare match, or clearing on compare match, or set. So this clears on compare match, this sets upon on compare match. So we have those various options. Okay, so timer or the timer 0, timer counter control register 0A is what sets all of this stuff. We have timer counter 0 control register B, which has some other bits that work. So notice here's that third bit that we were looking for. It's like, why did they stick it over here? Who knows? But anyway, there it is, and that's where you have to look for it. So, or actually, that's where you don't have to look for it. You have to set it. Okay. CS is the clock select. So this allows you to choose the frequency that you'll be working with. And FO, those are force output compares for A and B in non-pulse width modulation modes. We're not going to be using much of those, but we will need to use the clock select bits. So the clock select bits, those 3 bits give us these options for a clock source. So these assume the internal clocks that are being used. Here, these assume that the external clocks are being used. And so our standard clock, or what is called clock I/O, this depends upon the overall Arduino clock frequency, in which case is 16 megahertz. So then we can divide that by 8, we can divide it by 64, we can divide it by 256, and we can divide it by 1024. And so we can get these different frequencies coming out. A frequency like this corresponds to a pulse period of 0.0625 microseconds, all the way, and here we have 64 microseconds per period. So period means it turns on and turns off. So that full time. It's not the pulse width, it's actually the period, which includes the pulse and then the zero time in between. So if you want to know how many pulses are in 1 millisecond, that there are 16,000 pulses in general in 1 millisecond for this clock division. In this case, if we divide by 64, that gives us 250 clock pulses per millisecond, and so forth. So it's often helpful to see it expressed this way, because we may want to use this for this kind of information in working with a specific problem where we want a specific frequency or period. Okay, so the mode clear, timer on, compare, match, basically we set the waveform generator mode bits this way. In this case, the CTC clears with respect to output compare register A, not output compare register B. So remember, output compare register A then sets the timing, but that does not mean output compare register B can't be used. It can. And so in setting the frequency, when you use this, it's common to use a toggle. And so if you use a toggle, that means to get the thing to work properly, you have to set the period in half to get the correct frequency. So that's something just to kind of keep in mind. Let's work through an example. In this example, we're going to see how to use the timer and counter to work with a particular situation. So the problem before us is the problem of creating a quadrature encoder simulator. Okay, a quadrature encoder simulator. So we want to create a quadrature encoder simulator that simulates an encoder with 500 pulses per revolution and outputs quadrature signals out on pins from timer 0. So we want to use timer 0, so the pins then require 2 pins. So a quadrature is something that generates 2 signals. So we saw earlier that with a quadrature encoder, it's very common to use optical encoder, which has a disk with slots in it, and 2 emitters that are specially placed, and 2 detectors that are also specially placed to receive those emitter signals. And so sometimes the beam will go through the emitter to the detector. Sometimes it will be blocked by the slots so that it is not seen by the detector. So we basically have a situation like this, where as time goes on, so if this thing is rotating at constant speed, then I will get a fixed frequency of pulses, okay, or fixed period of pulses. Okay, so again, period and frequency are inverses of one another. And in quadrature, these 2 signals are out of phase. Okay, so one turns on and the other turns on, or this one turns off and this one turns off a little bit later. Okay, and so we saw these things working with optical or encoders. We see these things in working with motors. It's a simple way of encoding data, encoding rotational information using digital pins, digital signals. Okay, so that's what the encoder is all about. So it's often helpful when you don't happen to have an encoder just like right here with you, to want to be able to at least have some signals to work with to test out for example, to test out an algorithm that would decode the encoder. Okay, so we often want to be able to, we're going to see that that's an important task as we go along in this class. And so we want to be able to decode an encoder. And so it's often helpful to have a nice signal that is doing what we want it to do, so that we can test the accuracy of our signals, of our decoder strategies. Okay, so we're going to assume the rotation is a constant speed of 10 revolutions per second. So each second it revolves. This thing is spinning 10 times, which is pretty fast. It's not like an engine, like your car engine that can run at 3,000 RPM. Okay, but it's still pretty fast here. Okay, so that's what we're looking at. So again, a 500 pulses per revolution, PPR, pulses per revolution, quadrature encoder at a constant speed of 10 revolutions per second. So pulses per revolution, revolutions per second. When you multiply those two together, you get pulses per second. And in this case, we get 5,000 pulses per second, which is basically 5 kilohertz. Okay, 5 kilohertz. So that's the frequency at which we will be receiving pulses. So this corresponds to a period. So 5 kilohertz corresponds to a period of 0.2 milliseconds. Okay, a period of 0.2 milliseconds basically toggles every 0.1 millisecond. So I get a toggle here, toggle there. So I get toggles every 0.1 milliseconds. And then I have these two signals that are off. They're offset by this distance, which is actually 0.05 milliseconds. So I actually have those numbers to keep track of. Okay, so when we talked about the toggling and how that related to the period, so here this is the period we need, which means we need a toggle here. So this toggling is half the period. Okay, so the period includes two toggles. Okay, so that's something we need to take into account here. So we've gone through, we've done that, we've taken this into account. All right. So now we're looking at the clock to see how many toggles. So we want to choose the clock select to see how many toggles there are in 0.1 milliseconds. So again, I have a toggle every 0.1 millisecond. The clock select determines how many clock pulses there are in 0.1 milliseconds. So we're gonna see what to choose for our prescale value. So these are the frequencies we saw before and their associated period. So in 0.1 milliseconds, earlier we saw 1 millisecond. In 0.1 milliseconds, this is how many clock pulses there are in 0.1 milliseconds. So this is how many clock pulses we would count in order to determine 0.1 milliseconds. So if we have no prescaling, that's 16,000. Here we have 200 clock pulses per 0.1 millisecond. Here we have 25. Here we have 6 and 1.5. So this is the number of clock pulses that we have per 0.1 millisecond. So often we would like to choose a fairly large value. The larger number of counts, the more accurate the higher the count, the more accurate our waveform generation will be. So for example, if we're off by 1 pulse, well, that's 1 divided by 200, which is like 0.5%. Whereas here, 25, if we're off by 1 count, that's like almost like 20% off. Okay, so generally speaking, the more counts. So it's like, well, why don't we use this? Well, if we use this only requires 8 bits. So we don't ever have to go above 8 bits in order to use this. So it's 200 is actually a good number. Anything above 100 is probably good. So 200 is really good. Less than 255 so between 100 and 255, that's a good choice to make. So we're going to choose this as our prescaler. Okay. Now clock 0 also has outputs on Arduino pins 5 and 6, which correspond to port D pins 5 and 6. So those are the pins we want to use. Okay, so here's our timing diagram. This is what we want to see. Okay, so basically here's our timer. It's going to count up to our output compare register A value. So basically, if we want it to go up to 200 counts, that would give us a period here of 0.1 seconds. And so basically, we can have our system toggle every time we do that. Okay, so we can, by using an output compare match, we can have our signals toggle. So here's output compare bit A, here's output compare bit B. Okay, so basically our output compare bit A is going to toggle every time, actually every time we reset to 0, it's going to toggle every time. So here it's 0, it becomes 1, it's 1, it becomes 0, and so forth. So it toggles. And so this overall period now, you can see, is 0.2 seconds. So the next time is 0.2. So that has the desired period we're looking for. Okay. Output compare register B now. So notice if we choose this output compare register B to be half of this, then this will toggle. This signal will toggle whenever we hit that value. Okay, so we can set it up so that it'll toggle whenever it hits that value. So it toggles here, it resets, it goes through, it comes back and hits it again, toggles, okay, and so forth. So it climbs up, this signal goes up and comes down when it hits it again. So notice even though it drops here, it doesn't actually hit that value. It actually jumps from 255 down to 0, so it completely misses that value. But it continues on, and it'll eventually hit here. So it'll hit here, here, here. It's always hitting when it's climbing. Okay, so, and each time it will toggle. And so by setting it up this way, we can see we get exactly the quadrature type of a signal that we would expect. Okay, so this is the timing that we would get. And so if we can set it up this way, then we in fact get the behavior that we want. We get the right periods. Okay, we get the relative displacement between these two, the offset. So it gives us a nice quadrature pair of signals. And these bits 0C, 0A, 0C, 0B. So this is actually port D pin 6. This is port D pin 5. And so these are actually connected to those values, and we can actually hook into them and use them. So registers and parameters. Output compare register A. So again, that we saw that back here. That's the value 200. We wanted to count up to 200. Again, why do we want that? That's this guy here. Okay, and so we notice that we have the clock select that we need is that value. So here's the clock select value that we need. So that's 200. This is 1/2 of that, 100. So to set it up in the mode that we want, here's the COM for A. Here's the COM for B. Those are the control things, bits that we need to set. And then here's the waveform generation mode bits. Okay, and these bits are in this register TCC R0A. This bit is in TCC R register B. And then these 2 bits are in register A, and then these 3 bits are in register B. So that's where all of these bits are located. So by knowing what we're supposed to select in order to get the kind of thing that we wanted over here, this kind of behavior, we know exactly what to pick for these bits, and then we can enter this code. So notice that all of this code only appears in the setup function, does not appear in the loop function, because once you set this up, it just goes. So I'm not going to be changed. In this case, I'm not changing anything about the frequency or anything like that. And so this gives us exactly what we need. So we set up port D. In this case, we set up port D to have clear. I'm sorry. We're just zeroing bits 5 and 6 by doing this. So that's, in a sense, initializing them. You don't have to do that, but it's often a good idea to go ahead and initialize those. And it's often a good idea to initialize those before you set the data direction. So you'll find that that's actually a good practice, is to initialize your port values before you set the data direction. So in this case, we're setting the data direction for port D, bits 5 and 6, to be 1. Okay, so that's what that's doing. We're setting both of those bits to be output bits. Okay, so now we're going to initialize and set up the timer in the counter timer compare match mode, and to set these bits to toggle. Okay, so we're going to first set the counter. We're going to initialize the counter to 0. It's always a good place just to know where you're going to start. Otherwise, who knows what's in that register? It should be 0, but anyway, if we set it to 0, then you know it's exactly 0. Then we set output compare registers A and B to their appropriate values. Okay, so we saw how that worked before, and so that's what those are. And then now we set the COM bits, and we set the waveform generator model bits. So again, notice we only have to set one of them. It's the 1 bit, because the others are 0. By default, they're 0. And actually, this process makes them all 0. So, and then we for our clock select, this is our clock select that we need. Again, we're only needing to set the bit 1. So this then is all the setup that's needed. And once you start this program, then it runs, and regardless of what's going on in the loop. Okay, so this actually sets up that simulator for the quadrature encoder at the desired frequency. Now, if you want to change the frequency, you can do that in a number of ways. Again, you can choose the clock. You can change the clock select. You can change the counter top value. Okay, so if you decrease that top value, it will change the frequency. So if we were to decrease this frequency down to 100, this value down to 100, and this down to 50, you would get a quadrature set of signals that would be twice as fast. Okay, so by going up to 100, it goes up. It goes up twice as fast to 100 than it does to go up to 200. And so you can see how that works. So we could easily modify this to choose a different frequency by choosing a different value here, and if necessary, choosing a different clock select value. Okay, so this then is a program that illustrates how to use the timer and counter, how to set things up to use the timer and counter for a specific purpose. In this case, we generated not just one waveform, but actually a pair of waveforms and a specific relationship between them. Okay, so all right, timer counter. So here are the registers that we're concerned about. Timer counter, register 0, register, here's the output compare registers, and here are all those bits and their defaults and all that kind of stuff. So those are the timer counter count values, output compare register A, output compare register B. In terms of the pins, now we're going to look at pulse width modulation, and so we're going to kind of turn our attention in that direction. Okay, so pulse width modulation. So the pulse width modulation is connected to certain pins on the ATmega 328, and notice that some of these are for port D, some of these are for port B. There are 6 pins altogether, which correspond to 6 pulse width modulation. And so timer 0 is 8-bit timer, timer 1 is 16-bit, timer 2 is 8-bit. In terms of pulse width modulation out, so I have the output compare bits A and B for each timer. And those bits are actually on the I/O pins. These are port D, pins 5 and 6. This is port B, pins 1 and 2. I don't know why it says BP. It should say PB, port B. But anyway, so here's notice this is port B, pin 3. This is port D, pin 3. So in this case, in these two cases, both pins are in the same port. In this one, they're in different ports. So that's why you got this guy kind of over here, off by itself. Anyway, so those are the pins that are used for pulse width modulation. Okay, so fast pulse width modulation mode produces the fastest pulse width modulation waveforms compared to either phase correct or phase and frequency correct. So we talked a little bit about phase correct. Phase and frequency correct pulse width modulation is yet another form of pulse width modulation. So not only phase correct but also frequency correct, and it's subtle but it's important. So so phase and frequency correct. The frequency comes in when you want to change the base frequency for the pulse width modulation, and there are reasons at times to want to do that. Okay, so all right, so in fast pulse width modulation mode, the timer count simply goes from the bottom 0, 0 to the top, which is either 255 or this number, and then it resets. So it just goes from 0 to the top, 0 to the top, and just resets. So that's what the timer does. When the count reaches the compare values, A or B, then the output compare bit is cleared. Okay? And then these are then reset when the counter rolls over. So that's basically how the fast pulse width modulation works in words. Here's what it looks like in a picture. Okay, so again, we have the up counting up to the top, and it resets. So this blue is the counter, what the counter does as a function of time. Here we have a compare value, an output compare value, either A or B. And so when the count reaches that value, it clears the output compare bit, okay, which is then reset whenever this hits the bottom. Whenever it hits the bottom, it is reset. And then it's cleared again, it's reset, it's cleared again, and so forth. So this is the signal that we would get in what's called the non-inverting mode. We can also have it in the inverting mode, which is just, these two are just the knot of each other. Okay, so the frequency of the up-down clock, so this counting, this frequency is given by the clock frequency, which is 16 megahertz, divided by 256 and n, where n is the prescaler. So before, we had just the frequency of the clock divided by n when we were working with the timer itself. But now, since we have this thing that's counting from 0 to 255, then that's where this number comes from. So we have all of this for pulse width modulation. Again, this is fast pulse width modulation. The duty cycle, okay, of the pulse width modulation signal depends on whether we have the non-inverting or the inverting version. Okay, so the non-inverting, we take the output compare register and we divide by 256. Okay, and so this gives us the duty cycle for this fast pulse width modulation in the non-inverting mode. This is what it is in the inverting mode. Okay, so we can actually compute the duty cycle, and so that's what we get. And this number is expressed in percentage. That's why the times 100 comes in here. So let's take a look at an example of fast pulse width modulation. So use fast 8-bit pulse width modulation. Here's the example. Here's the problem. We want to use fast 8-bit pulse width modulation. We want to use both A and B on timer 0, so both channels. We want to clear the output compare bits on compare match. Okay, so we want to use this clear output compare bits on compare match and set on top. We want to choose a pulse width modulation frequency approximately twice the default pulse width modulation frequency. So approximately 1 kilohertz. Okay, so this is what we want to do in our pulse width modulation example. So when you use analog write in the Arduino IDE, you're actually choosing kind of a default setting for pulse width modulation. That's just one of actually many possible settings for pulse width modulation. So we're going to do something a little different. In this case, we're going to do something a little higher frequency. So the default pulse width modulation frequency for the Arduino is about 500 hertz. Actually, not quite 500 hertz, like 490 something. So we're going to choose. We want to choose something approximately twice that. Okay. So you'll find when, for example, when you hook up a motor to the pulse width modulation, you can actually hear the motor humming because of the frequency of the pulse width modulation. So, and if you change the frequency, it'll basically hum at a higher frequency. It's very common for industrial pulse width modulation systems to actually use a very high frequency, like tens of kilohertz. And so when you use those frequencies, it's actually humming. The motor will hum, but it'll hum at a frequency you can't hear. So it's not disturbing to you. Otherwise, the humming from a motor when you're using pulse width modulation can get kind of annoying. Okay, so here are the frequency possibilities that are available to us by appropriate choice of clock select. So that's clock select. So remember, we have these frequencies, these base frequencies, and when we use that formula, these are the possible frequencies that we can get for the fast pulse width modulation. So we see, for example, I can get 62 kilohertz. I can get 7.8 kilohertz. Here's approximately 1 kilohertz. Then this is 244 hertz, 61 hertz. So this is the closest one to 1 kilohertz. Okay, that's the closest one that we have. Okay, to set things up the way we want, again, we'd set the counter to be 0. This is what we would choose for channel both A and B. Again, these appear in the timer counter control registers 0A. W, the waveform generator mode bits are this. Notice the X here means it doesn't matter. If you have these two guys set to be 1, 1, it doesn't matter what that bit is. So in general, we'll leave that 0, and then we don't have to do anything with it. Again, these would be in these registers. This bit would be in this register, but we're going to choose it to be 0, in which case we don't do anything with it. And then our clock select, we saw from our previous page, these are the values that we need to choose. And again, those appear in this timer counter control register B. Okay, so we now, given the problem, we now know what settings to choose for these various bits that we need to set. So we can use this control program to set the timer up. So here, again, we're going to initialize port D to be all zeros. And then we're going to set the data direction for bits 5 and 6 to be output bits. Here, these have the bits that we need to set WGM and to set the other set. So these are the settings that we need in order to get what we were hoping to get. So here are our clock select bits and so forth. And we're going to set the timer to be 0 to start off with. Now in your loop, in general, in pulse width modulation, you're changing your duty cycle. Okay, and we saw the formula for the duty cycle and how it was based on basically OCR 0A. So depending on what we choose for OCR 0A, that will affect the duty cycle for A. And if we choose a different value for B, it'll choose the duty cycle for B. We weren't told what to do with that at this point, but we do have a formula for what will determine the duty cycle. Okay, so this is a fast pulse width. This will allow us to set up fast pulse width modulation. Okay, so there we are. That's the example. We move on now to talk about phase correct pulse width modulation. So again, phase correct pulse width modulation produces what would be called symmetric waveforms. These provide smoother motions when used with motors. Okay, the center of each pulse occurs at the period. Okay, so the center of each pulse those centers are evenly spaced, as opposed to the falling edge of the fast pulse width modulation. In this case, instead of just counting up all the time, it's actually counts up and then counts down. So we have a different kind of counting that's needed. And so as a result, the frequencies are basically half of that used for fast pulse width modulation. So that's what it is in words. Here we have it in terms of a diagram. So again, we're counting up and then we count down. We count up and we count down. And so wherever we have our output compare value, wherever it crosses this triangle wave, so when it crosses going up, it clears. When it crosses going down, it sets. Okay, and so you can see that if this green line were all the way up, it basically clears and sets like right next to each other, and it basically leaves it a constant high. So the higher this value is, the longer the pulse is set. Okay, so the going up, we get a clear. Going down, we get a set. And so that's basically what happens in this phase correct. So the center of each pulse is when this hits bottom. Okay, and that center, those centers are evenly spaced. They're periodically spaced, and so the pulse is centered around those points. So this gives us a symmetric pulse width modulation. So here's the frequency for the pulse width modulation. Notice that it's divided by not 256, in this case by 510, which is kind of interesting. It's not 512, it's 510. But anyway, this is what we have. Again, n is our prescaler, and this is the formula for our duty cycle. Okay, so in this case, it's actually simpler than the other one. In the other case, we had the output compare register 0 A plus 1 divided by 2. So we don't have that plus 1. So this is the duty cycle that we get for the normal or the non-inverting mode and for the inverting mode. So our phase correct pulse width modulation then has these frequencies. So these frequencies are in fact exactly half of what we had for the phase correct pulse width modulation. I'm sorry, the fast pulse width modulation. And so this is actually the standard frequency used for pulse width modulation when you use the analog write command. So it's not exactly 500 hertz, it's 490 hertz, but it's close to 500. So these are the frequencies that we would use, that we would work with if we were to use the phase correct. So in some ways, the phase correct gives you a nicer pulse width modulation, but it is slower. So you have some trade-offs. Again, we could also change the number of clock pulses or the frequency and still work with this thing. So we still have some variation. We have some tweaking we can do, and it's always helpful to have that if we need it. So if we don't need it, then that's okay. But if we do need it, it's nice to have it. So this is a very overview, a very fast, in some ways, a fast overview of the timer and counter details for the Arduino. A lot of stuff going on here, a lot of timers, registers, a lot of things to keep track of. So I recommend that you become thoroughly acquainted with this material, because it will help us later, and particularly when we talk about interrupts. When we talk about interrupts, it's going to be important to understand what's going on in the timing and all that that's associated with what we're doing. Thanks for watching.